Hey math fans, Alex here, and today we're going to talk about something called mathematical expectation. So to motivate this idea, consider the random variable x with the following PDF. Okay, so x could take on the values from -2 to 2 with these probabilities. And what I want us to do to start off with is I want to compute the following sum. So we're going to sum over all possible x values. And what we're going to sum is x times the probability of x. Okay, so this is a fairly basic sum to compute. All we have to do is take each of these x values, multiply it by the probability, and then we're going to add all these up, right? Because it's a sum. So this is -2 times 0.1 plus -1 times 0.2 plus 0 times 0.2 plus 1 times 0.2 plus 2 times 0.3. Okay, and what do we get? We get negative, let's see, -0.2 minus 0.2 plus 0 plus 0.2 plus 0.6, which is 0.4. Okay, so it looks fairly basic. But what this kind of gives a sense of is, on average, where the random variable lies. Okay, so you wouldn't expect the random variable to have an average of 0 because the probabilities are weighted slightly towards the right side, where this guy has a 30% chance of occurring. So you'd expect it to be a little higher than 0, which is about 0.4. Okay, so in this sense, what we've just done is kind of defined the quantity where if you sum over all possible x values and you sum x times the probability of x, I should say the probability that x is equal to little x, this is, you know, a weighted average of sorts. Which we call the expected value of x. Now, formally, I should probably, actually define it. So maybe we can call this a definition. Okay, so I'll use the same term again. So the expected value of x, sometimes called the expectation value of a random variable x, which we denote as, it's essentially a function. It's going to be a function of the random variable. And you'll see a lot of times these brackets. Okay, but I'm kind of lazy and I'm going to be doing this a lot, so sometimes I'll also just put them in parentheses. Okay, so denoted e of x is defined for discrete variables, which is the only kind that we're going to be considering today, as follows. The expectation of x is just going to be the sum over all x of x times the probability, and that x is equal to little x. For continuous variables, it's very, very similar, but I want to define that separately in a different video. Okay, and there's a caveat, right? This could potentially be an infinite sum. Okay, so what could possibly go wrong? Well, the sum could fail to converge. Okay, so the sum, I'm actually going to go ahead and put from -infinity to +infinity of x times the probability of, I'll just put little x. That has to converge, but not only does it have to converge, but I have to say that it has to converge absolutely. Okay, so remember that a sum converges absolutely if the absolute value of it converges. Okay, so i.e., I'll just put over all x. The absolute value of this has to converge, but remember I can split the absolute value up into the absolute value of x times the absolute value of the probability, but the absolute value of the probability is the probability. probability is positive, so I don't need absolute values there. Okay, so really this is just saying that the sum of the x's in absolute value times the probability, that whole sum has to be less than infinity. Okay, so that's just kind of a small caveat. Now, I want to introduce kind of another concept, and it's going to be related to expected value, but let's go ahead and define. So let's define the random variable y as a function of the random variable x given above. Okay, where x was defined above, and I'll just go ahead and put that again on here just for reference, that this was the PDF of x. Okay, so we want to try to relate the probability of x with the probability of y, and we want to relate the expected value of x with the expected value of y. We're going to notice something kind of interesting. So, what would the probability density of y look like? Okay, well, clearly the range of y is going to be very different from the range of x. If these are the only possible x values and I square them, I'm only going to have, let's see, 3 possible y values. Okay. So, I could possibly have, let's see, 0, I could have 1, and I could have 4. That is it. Now, what are the probabilities of those? Well, the probability of, say, 0 occurring, for example, that could only happen in one way, right? 0 could only happen in that way because 0 squared is 0. So that probability is clearly just going to still be 0.2. Now, how about 1? Well, for 1, there are going to be 2 possible ways I could get 1. Right? The first way is I could have my random variable x take on the value -1, or I could have my random variable take on the value 1. Okay, so I have to add those probabilities together because that could happen 2 different ways. So these are going to kind of combine to give me this probability, which is going to be 0.4. Lastly, I have 4, which can, similarly occur in 2 different ways. Okay, so I'll do this in maybe blue. I could have -2, or I could have a +2. When squared, give me 4. So I take these probabilities and combine them to get me 0.4 again. Notice that, just like a PDF, normalization still happens because all 3 of these add up to 1. So that's the probability density function of y. Now let's go ahead and find the expected value of y. Well, by definition, the expected value of y is what happens when you sum over all possible y values in the range of y times the probability that y is equal to y. Okay, so this is going to be a sum consisting of only 3 terms, right? You could have 0 times 0.2. You could have 1 times 0.4. Or you could have 4 times 0.4. Okay, so let's see. That gives you 0 plus 0.4 plus 1.6, which gives you 2. Now, it would be pretty miraculous if the expectation value of x equaled the expectation value of y. These are weighted averages, right? And clearly, the weight is going to be over here, probably somewhere between 1 and 4. So there's no way that the expectation value in general of a function of x is going to equal the same thing as x. That's just unrealistic. However, there is a little interesting shortcut that we can apply to this, because it's kind of a lot of work in general if I give you y as some kind of function of x to find the expectation value of a function of x. Okay, however, this little theorem of sorts kind of gives it to us. So, note, all caps, note, let's find the following sum. We're going to sum over all x, but this time instead of x times the probability that x is equal to x, I'm going to replace this with f of x, which in this case was x squared, right? Let's go ahead and find that. Well, okay, we have to sum over all possible x just like before. So if you'll recall, these were the possible x values. We had -2, -1, 0, 1, and 2. And we have to square them. So we're going to have -2 squared times the probability, which was 0.1, plus -1 squared times, I believe that was 0.2. Right, everything else was 0.2 except the last one, plus 0 squared times 0.2, plus 1 squared times 0.2, plus 2 squared times 0.3. And if you do that, you will get 2. That's interesting. I got the same thing for the expectation value of y as I would have gotten if I replaced the x with my function of x. So in other words, in a way, this could possibly be, the expectation value of x squared. And if you notice, expectation of x squared, all I did was I replaced this thing in front with an x squared. That seems like a coincidence. I don't believe in coincidences. So, turns out that this is true, and we're going to go ahead and prove it. So, I'm not going to call this a theorem. Maybe we'll just call it maybe a property of, the expected value. Okay, and this is also called the law of the unconscious statistician, or sometimes the law of the lazy statistician, because it's something that we take for granted a lot. And in fact, the first book that I learned probability from just said this as a definition, which I think is a little misleading because there's really nothing obvious about this at all. But we're going to go ahead and let y be some function of the random variable x. Okay, then we have that the expected value of y, which is the same thing as the expected value of this f of x, that's going to equal the sum over all x still of f of x times this probability. Okay, so that's what we're trying to prove. Okay. I will give a proof of this for the discrete case. The continuous case is a different proof altogether, and it's really kind of beyond the point that I'm trying to make. But let's go ahead and try to prove this. Okay, so for the proof, the first thing that I would like to note is that in general, there has to be a function taking these x values to these y values, but that function needn't be one-to-one, which means it's very possible that you have two possible x values going to the same y value. Okay, so what we're going to do is we're going to consider each y value separately, and we're assuming, of course, in the discrete case that if we're summing over all x, it is a countable number. So we can just count every single y value in this case and look at what's called the preimage. Okay, so in this case, just as an example, the preimage of what we call the set y1, which I'm just for convenience just going to drop the set notation and just say that the preimage of y1 would be the points x1 and x2, because x1 and x2 map to y1. Okay, so both of these are in the preimage of y1, and likewise, we might have these two both be in the preimage of y2. We can't have a situation like this. We can't have one thing go to two things. That doesn't make sense. That wouldn't be well defined, but we can have something like this. Okay, so that's going to help us out. All right, so to start, I just have to be very careful with the summations. It's really the trickiest part of this. So we're going to start off by summing Okay, so the expectation value of y is going to equal the sum where we are actually going to consider all y sub i's in the set B. Okay? And we're just going to sum, by definition, each y sub I with the probability that happens, that y is equal to y sub I. Okay? So nothing fancy so far. But what I have is that this probability that y is equal to y sub I can break that down a little bit more, okay? And that is actually going to be the sum of probabilities of everything that maps to y sub I. Okay, let's look at the example above and let's figure out how I got this PDF in the first place. How did I get this as the probability? I looked at everything that mapped to 1, which were these two, and I added the probabilities. Okay, so the probability that y is equal to a given y is going to be a sum of probabilities of all the x's mapping to that y. Okay, so let's write that down a little bit more formally. So this is going to be a sum over all y sub I in B of y sub I times, I'm going to write that this is a sum of all, of all x's that are in the pre-image of that y sub I. So I'm summing over all the x's that map to that particular y value, and that is going to be all the probabilities that x is equal to that x. Okay? Now, at this point, I can go ahead and move this y sub I back in this original sum. So let's go ahead and do that. So this is now going to be equal to the sum over all y sub I in B over the sum of all x in the pre-image of each y sub I of y sub I times the probability that x is equal to x. Now, y sub I has to be f of some x value if it's in this sum. Okay, so this is actually going to go ahead and be, still have the sum of all y sub I in B, sum over all x in the preimage, that y sub I. So if y sub I exists here, that means that we can rewrite it as f of some x and just sum over all those possible x's, right? So y sub I just equals f of x for a bunch of x's, for all of these x's, in fact. It's actually the same thing, right? So I can go ahead and just replace this with f of x. This is going to be just f of x times the probability that x is equal to x. And I'm almost done now. This double sum can be replaced with a single sum if you kind of understand what's happening here. Okay, so this is summing over all y sub I in B, and this is summing over all x that's in the preimage of a particular y value. Okay, so what is that doing? Okay, just to give you kind of an example here. So I'm taking this y sub I value, and I'm looking at summing over all x's that map to that. So I'm summing over both of these. Okay? That's what this says. This says for a particular y sub I, sum over everything mapping to that. This sum says, oh hey, and by the way, go ahead and do that for every single y value. Go ahead and sum over all the x values. Well, that's just equivalent to summing over every single x value individually. And since our sum is now solely in terms of x, that's exactly what I'm going to do. So I'm going to replace that double sum. I'm justified now in replacing that with a single sum of just summing over all possible x. And really, if you want to be more specific, it's really all x in the set A, as I've denoted it, of f of x times probability of x given x. Right? All right, so conclusion that we often take for granted, the expectation value of a function of random variable x is just the sum over all x of f of x times the probability of x. Right? Okay. Last remark that I'll make before listing some properties of expected value is this works for joint PDFs as well. Okay, so let's go ahead and let z be a function of both x and y, with x and y random variables. Okay, then I think it's pretty natural to understand, okay, with joint PDF, sorry, which we'll call, p xy of xy. Okay, then it should be pretty natural to understand that the expectation value of z, which is actually the expectation value of this function of both x and y. From the previous, it's understandable that we're going to essentially be summing over all x and all y of this joint function. Let's see, f of xy times the probability of xy. So it works for joint as well. All right, so I'm going to go ahead and list some properties of expected value, and then we're going to prove most of them. All right, so here are the properties of expected value. I know it seems like a lot, but quite honestly, all of them are important. We're going to use all of them, so just know them. Okay, I'm going to go ahead and just prove as much as I can over here just to save some space. And since all the properties are written right here, let's get started. So the proof of 1, the expectation value of the random variable 1 is equal to 1. What's the random variable 1? Well, go ahead and define the PDF of this random variable of 1. We're just going to go and define that as the value 1 if x is equal to 1 and 0 otherwise. It's kind of like the constant function, but everything just maps to 1. Okay, so by that logic, then the expectation value of 1 is equal to the sum over all possible x of 1 times the probability that x is equal to x. Well, the only time the sum is going to be non-zero is if x is equal to 1. Okay, so we can go ahead and drop the summation, and it's only going to have one term, which is 1 times the probability that x is equal to 1. Okay, which by definition is 1. So we get 1 times 1, which is 1. So that proves number 1. Number 2, the expectation value of c times x, I'm going to leave that as an exercise. You're essentially going to pull the constant out of an infinite sum, and you're going to get the expectation value pretty directly. All right, the third one, the absolute value of the expectation value, well, let's go ahead and plug that in. Remember, that's going to be this infinite sum over all x of x times probability. I'm just going to put a little x. Now, this is going to be less than or equal to the sum of the absolute value of x, p of x. And this is by the triangle inequality. And if you're not familiar with that from analysis, then I recommend Googling it. It's by the triangle inequality. If anyone has any proofs of this that don't rely on this inequality, I'd love to hear them. Okay, but then remember, I think we talked about this before. This is technically the same as the absolute value of x times the absolute value of the probability, but probability is always positive, right? But yeah, so we can just write that as p of x. But if we let this be the function, f of x equals the absolute value of x, Well, then this is just the expected value of f of x, which is the absolute value of the random variable x. Okay, so this thing is always going to be less than or equal to this thing. Okay, 4 is probably extremely important because 4 alongside with 2 gives us linear combinations. And I might do a quick example of that. Okay, so the expectation value of the sum is, this is wrong. This should be the sum of the expectations. Okay, let me just correct that really quickly. This is worth proving. Okay, so I'm going to start off by just writing down the definition again. Okay, so this is going to be what? Well, it's going to be it's a joint distribution, right? And we defined what it would be for a joint distribution right here, right? It would be, the sum over all possible x's and y's of the PDF times that. Okay. But for the discrete case, you have a very nice formulation for what this is. Okay, so this is going to be double sum for all x and all y of little x plus little y times the probability that x is equal to x and y is equal to y. And I don't know what that probability density function is. It really doesn't matter. Okay. Okay. So now I'm going to do what? Well, I'm going to distribute the x and the y. Okay, so I'm going to, well, basically what I'm going to do is I'm going to distribute this into both x and y. Okay, so this gets me this double sum. Let's see, x times this probability plus y times this probability. Okay. But now I can break the sum up, right? If these are kind of a double sum, I can break that up into double sum of just x times this guy plus this double sum of just this guy. Okay. Now I can start pulling some stuff out. Let's see, what can I do? Trying to think. I can pull this y outside of that sum. Okay. And also what I think I'm going to do is I'm going to go ahead and swap the order of the summation right here. If we're summing over all possible x and y, it doesn't really matter the order that I sum them in. It's kind of like double integrals, right? dx dy, dy dx. One might be easier than the other. Okay, so two changes that I'm making. One over here, I'm actually going to sum over y first. Okay, so I'm going to note that as a change. Then I'm going to go ahead and factor this y out. Okay, plus sum over all y of y, and then the sum over x of probability of x equals x, y equals y. Okay. Now, I can do the same kind of idea. I can pull this x out, but it's essentially going to be the same thing as what I'm about to do here. So I'm summing over every possible x of the probability that x is equal to x and y is equal to y. Okay, but this is a marginal distribution, and I know I only talked about that in the continuous case, but it works just the same for the discrete case. Okay, so this is a marginal marginal distribution. And this is actually just equal to the probability density function of y, right? Because summing over all possible x gets me 1. So I'm just left with the probability that y is equal to y. Okay, so this is going to work out the same, and you can kind of fill in the details. But what you're going to be left with is you're going to be left with x times, well, no, you're going to be left with a sum over all x of x times the probability that x is equal to x, because this marginal distribution is going to be over x, plus the sum over all y of y times the probability that y is equal to y, because you're going to get this marginal distribution, which is just the expected value of x plus the expected value of y. Okay? All right. Now, since we proved all of those, 5 is going to be pretty straightforward. Remember, 5 was if x is less than or equal to y, we're going to show that the expected value of x is less than or equal to the expected value of y. But what we're going to do is if x is less than or equal to y, then we know that y minus x has to be bigger than or equal to 0. Okay. So if a random variable is non-negative, the expected value is also non-negative. You should really prove that, again, as an exercise, but it's not really hard to see. So this also has to be non-negative. But we just computed what this guy is. Okay? So that's going to imply that this is going to be what? This is going to be the expected value of y plus the expected value of negative x. Okay, but according to one of the properties, this is a constant, and I can pull that out. Okay, so we're using all these properties. This is the expected value of y plus a negative expected value of x. And then since these are numbers, just add the expected value of x to both sides. We get what we wanted. The expected value of x is less than or equal to the expected value of y. Okay. Last one. That one said if x and y were independent, that's going to imply that the expected value of xy was just equal to the product. Something else that we are definitely going to use a lot. And I'm probably going to do this in a different color. So go ahead and let x and y be independent. Okay. Then x times y is a joint probability distribution. So by definition, the expected value of x times y is equal to the sum for all x and y of the product xy times this joint distribution. Okay, but since x and y are independent, we can go ahead and write this as probability x is equal to x times the probability that y is equal to y. Okay. Okay. That's pretty clear what we're going to do, right? From here, we're just going to pull out all the y's. Right? So that's a y, that's a y thing. All those are going to go outside of the x summation. And we can just leave the x's alone. So this is going to be the sum for a y times py of y times the sum of x for x times px of x, which is the same thing as I'm going to reshuffle the order, the expected value of x times the expected value of y. Okay, so that's it for discrete expected value. In the next video, we are going to talk about the continuous case and possibly do some examples. Hope to see you there.